United States Battery Circular Economy and Princeton NuEnergy's PNE South Carolina flagship recycling facility are pioneering a revolutionary approach to resource management. This transformative strategy tackles environmental concerns while securing domestic supply chains for critical materials. As electric vehicles and renewable energy storage systems gain prominence, the ability to recover and reuse battery materials becomes a strategic priority with far-reaching implications. Let's dive into the concept of the battery circular economy, a sustainable framework for managing the entire life cycle of batteries, from production to end-of-life processing. This closed-loop system prioritizes the recovery of valuable materials from spent batteries and manufacturing waste to create new battery components. By doing so, it significantly reduces the reliance on newly mined raw materials, addressing environmental issues and supply chain vulnerabilities. Keeping materials in productive use for extended periods maximizes resource efficiency and minimizes waste. Dr. Chao Yan, co-founder and CEO of PNE, emphasizes, "In Chester, we demonstrate that the United States can lead in battery materials recovery and manufacturing, not just in the future, but right now." This statement highlights the immediate practicality of this innovative approach. To fully comprehend the battery circular economy, consider these essential components. A collection infrastructure for gathering end-of-life batteries and manufacturing waste. Sorting facilities capable of distinguishing between various battery chemistries. Advanced recycling technologies that maximize material recovery rates. Refining processes that convert recovered materials into battery-grade inputs. Manufacturing capabilities that successfully reintegrate recycled materials. This integrated ecosystem necessitates cooperation between battery manufacturers, recyclers, material processors, and end users to function optimally. Each element is crucial in ensuring that materials retain their highest utility and value throughout multiple life cycles. Why is battery recycling pivotal for the United States? It's about reducing dependency on foreign material sources. The U.S. faces significant challenges concerning battery material supply security. Most critical minerals used in battery production, such as lithium, cobalt, nickel, and manganese, come predominantly from overseas sources, creating potential vulnerabilities in supply chains essential for the energy transition. Battery recycling offers a domestic alternative by recovering these materials from batteries already in the country. This urban mining approach transforms waste streams into valuable material sources, decreasing reliance on international suppliers that may be influenced by geopolitical tensions or market volatility. Moreover, the environmental benefits of battery recycling are undeniable. It reduces waste, conserves resources, saves energy compared to primary extraction and processing, preserves land by minimizing the need for expanded mining operations, and conserves water through closed-loop processing systems. While precise environmental impact measurements require comprehensive life cycle assessments, the general principle is clear. Recovering materials from existing batteries generally demands significantly less energy and produces fewer emissions than extracting and processing virgin materials. The economic opportunities within the recycling sector are vast. Beyond environmental and security advantages, the battery recycling industry presents a significant economic opportunity for the United States. As domestic battery manufacturing capacity expands, driven by electric vehicle production and renewable energy storage deployment, recycling operations offer complementary growth potential. The sector generates high-skilled manufacturing jobs in materials processing, chemical engineering, and advanced manufacturing. These positions support both immediate employment and long-term workforce development in technologies essential to the clean energy transition. Furthermore, localizing material recovery reduces transportation costs and market volatility for battery manufacturers, potentially enhancing the cost competitiveness of American-made energy manufacturing products. Ongoing advancements in battery recycling processes continue to improve efficiency and cost-effectiveness across the industry. How does PNE's South Carolina facility reshape the U.S. battery landscape? It's the nation's first commercial-scale, advanced black mass and battery-grade cathode active material production facility, showcasing that domestic processing of battery materials has evolved from theoretical potential to practical reality. The facility boasts a current capacity of 5,000 tons per annum, TPA, with plans to expand to 15,000 TPA by 2026, and a scalable design allowing growth to 50,000 TPA as market demand increases. It handles both NCM and LFP battery materials, adhering to full environmental compliance with all U.S. and state standards. This scalable approach enables PNE to align processing capacity with growing battery waste volumes as electric vehicle adoption accelerates and the first generation of grid storage systems reaches end of life. The Chester facility leverages proprietary advanced recycling processes that achieve recovery yields exceeding 97%, surpassing typical industry recovery rates. This efficiency maximizes the economic value extracted from each ton of battery waste while minimizing residual materials requiring disposal. The facility produces advanced black mass, ABM, a consistent, high-purity precursor material suitable for further refining into battery-grade materials. Strategically, the facility demonstrates immediate U.S. capability in advanced battery materials recovery at commercial scale. Addressing a critical gap in America's battery supply chain, it provides a working model for future recycling operations across the country, potentially accelerating industry development through demonstrated success rather than theoretical potential alone. What sets PNE's approach to battery recycling apart? Their direct recycling technology preserves more of the structural integrity and value of battery materials compared to conventional methods. Traditional recycling often relies on energy-intensive pyrometallurgical processes that destroy the chemical structures of battery components to recover base metals. In contrast, direct recycling aims to recover cathode materials with minimal structural degradation, requiring less energy while producing higher quality outputs. This approach yields materials suitable for immediate reintroduction into battery production with fewer intermediate processing steps. PNE's South Carolina facility's exceptional recovery yield, over 97%, showcases the effectiveness of these advanced methods in maximizing material utilization while minimizing waste streams. The facility's multi-chemistry capabilities provide critical flexibility as manufacturers shift between different cathode formulations based on performance requirements, material availability, and cost considerations. Rather than requiring separate facilities for each chemistry, PNE's approach allows adaptation to changing market conditions and technology trends. PNE's comprehensive quality control systems maintain consistent output quality from variable input materials. These systems include material traceability throughout the recycling process, rigorous testing protocols to ensure consistent output specifications, third-party validation capabilities through their Princeton Materials Testing Center, and downstream application testing to verify material performance in actual battery cells. These quality assurance measures bridge the gap between recycled and virgin materials by demonstrating that recovered materials can meet the stringent requirements of battery manufacturers. PNE is building a national battery recycling network through strategic facility locations across the United States. This includes a flagship commercial-scale production facility in Chester, South Carolina, a joint pilot facility in McKinney, Texas, advancing direct recycling technologies, and a materials testing center in Princeton, New Jersey, described as the largest in the U.S. Northeast. This distributed approach establishes regional capabilities aligned with battery manufacturing hubs while maintaining centralized technology development and quality control functions. The geographic diversity also reduces transportation requirements for battery waste materials, which can face regulatory challenges when shipped long distances. PNE's expansion plans follow a phased growth strategy, starting with 5,000 TPA initial capacity, expanding to 15,000 TPA by 2026, and scaling to 50,000 TPA as market demand increases. This incremental approach allows for capacity expansion, timed to match growing battery waste volumes, while managing capital requirements efficiently. The potential capacity highlights the anticipated growth in recyclable battery materials as electric vehicle adoption accelerates. However, the U.S. battery recycling industry faces several challenges. Collection and logistics hurdles involve developing efficient collection networks for diverse battery types, navigating transportation regulations for potentially hazardous materials, managing batteries of varying states of charge and degradation, establishing standardized disassembly protocols for different vehicle designs, and creating tracking systems to monitor battery chain of custody. Technical processing challenges include design variation, chemistry evolution, material segregation, contaminant management, and quality consistency. Market and economic considerations involve fluctuating prices for recovered materials, competition with primary materials, establishing reliable supply agreements, and securing investment for recycling infrastructure. Despite these challenges, battery recycling supports U.S. climate goals by reducing the carbon footprint of battery production and contributing to the clean energy transition. It addresses sustainability concerns and ensures material availability for expanding energy storage deployment, essential for integrating higher percentages of intermittent renewable energy sources. Policy alignment with environmental objectives, such as reducing greenhouse gas emissions, minimizing hazardous waste disposal, creating domestic manufacturing jobs, and reducing dependence on imported critical minerals, further strengthens government support for recycling initiatives. The future of battery recycling in America holds emerging technologies and innovations, projected growth and investment trends, and integration with broader circular economy initiatives. These developments will maximize material recovery, minimize environmental impact, and facilitate the clean energy transition.